Okay. Is everybody here in this group?
I believe so.
We're good? Okay. All right. Well, thanks for coming out. I'm not going to give you the economic side that you've already had plenty of, I'm sure, and to some extent the environmental side. But in the big picture, well, one of the things I wanted to take a little different slant on was society as a whole is moving towards electrification of everything, okay? Yes, I know we just got maybe a pipeline going out to the West Coast, but overall, we're moving towards electrification. That's going to be a problem. One, in as much as how much the grid can actually handle, okay? So one of the things we can do is reduce the amount of electricity we consume, both from an economic perspective, all the tax benefits, so on and so forth, but just the sheer cost of the bill and the amount of energy. If we reduce it, we also give a little relief to the environment as well. So both of those just make sense. What's the best way to start? Reduce how much you use. Tighten up the envelope. That's number one. Biggest bang for the buck, okay? You can use some technologies like LED lights and lose some of the other higher cost appliances we're used to using, the more modern technology. And leverage your electricity or your energy consumption wherever you can. And one good example of leverage is a heat pump, okay? So we can take the electricity that we use in that heat pump and we can multiply the amount of actual heat energy we get out for the building. That's good. I mean, that's be like nice kind of an investment, wouldn't it be? Anyway, so what I want to do for today is on that theme of leveraging our electrical costs and our electrical consumption and running it right into this heat pump. So first thing, little review. Which way does heat flow? So you're got no glove on, it's 30 below, you grab the car door handle, you know which direction heat flows. Hot to cold, right? Warm to cool, cool to cold. So that's the direction from higher temperature to lower, right? Okay, next thing is refrigerators, freezers, air conditioners, water coolers, all heat pumps. They're all heat pumps. Even the one air conditioner in the window, if that's what you had, it's a heat pump, okay? So it's not new. The technology has been around, it's understood, it's straightforward, all right? So in your refrigerator, do we add cold or do we remove heat? And we remove heat, and you know that. It's cold inside, but it blows warm air out under your feet or at the back of the refrigerator or freezer. So you took heat from here and you just moved it over there. That's all you did, okay? All right, it's a heat pump. That's what it does, moves heat. So anybody here pump up a bicycle tire by hand? Okay, all right. Is there a difference between, you might not know this, pumping up a mountain bike tire and a road bike tire? That's really getting technical now. Much harder to pump a road bike tire because it's higher pressure. Regardless, as you pump up the tire and as the pressure builds, it gets harder and harder and harder to pump. What else happens? The pump gets warmer and warmer and warmer. You ever notice that, especially a road bike? You grab the end of the pump, holy smokes, this is hot. So all this air that you started with in the cylinder of that pump, you squashed it down, okay? As you squashed all the air down, well, there was heat in that air. Well, you squashed it down too. So you concentrated the heat, intensified the heat, temperature goes up. So keep that in mind. When you compress something, it's a gas, its temperature goes up. Make sense? Okay. It's not new. It's every day if you've worked with a bicycle pump. So you're outside, nice windy cold day, one hand's wet, one hand's dry. Which one's colder? The wet one. Why? Because when liquids evaporate, they absorb heat, a lot of heat. Okay, whenever a liquid evaporates, it absorbs a lot of heat. And it takes it from your hand if your hand is wet. Ice fishermen will tell you that. Okay, the one that just about got off the hook, got to go in, and now his hand's wet and it's 20 below. All right, so when we evaporate a liquid, we absorb a lot of heat. You already know that. All right, So in this heat pump, we've actually got a system of 3 closed fluid loops. We got one loop here. This is our ground loop. We'll come back to it. We got a refrigeration loop, and we've got a production loop. This is called a water-to-water heat pump. Does that make sense? Okay. All right. So we're going to do one loop at a time, and then we kind of tie it all together. So let's say this loop has 3 degrees C water coming out of it, and there's a circulation pump. That's this red pump right here. These are those loops kind of modeled, okay? These are the loops here. So we circulate 3-degree water into the ground that's sitting at 7 or 8. Which way does the heat move? From the ground into the water in the loop, okay? And water holds a lot of heat. So there's a lot of heat gets absorbed into that loop from the ground. So the loop now comes out at 7. Went in at 3, comes out at 7. And we absorbed it from the ground, a big heat battery down there, right? Okay, so from there, it wraps around part of the refrigeration loop, the part called an evaporator, okay? Now, these are not physically connected, but they're thermally connected. We call them heat exchangers. So they're in thermal proximity to one another, okay? Now let's look at this refrigeration loop that we talked about. So you've got a refrigerant, a gas in there that boils at the temperatures we like it to boil or evaporates. It's chosen for that. And we got this compressor up here. The compressor takes in cold gas and it squeezes it into the condenser side against a restriction, an orifice, okay? And so we end up with high pressure here, low pressure there. And I won't go into all of the details why that is, but that's what happens. So now, if we've got a refrigerant flowing through this loop and it comes in at -5 as a liquid, okay? And it goes into this evaporator and it starts boiling. Well, boiling liquid absorbs a lot of heat. Well, this is -5, that's +7. Which way is the heat going? It's going from the water loop into the refrigerant because it's boiling, it's evaporating. And the refrigerant's now a gas at 0. Does that make sense? Started out as a liquid at -5, it's a gas at 0. It's got a lot of heat in it. But that is not going to heat your house. That's a problem. We've absorbed a bunch of low-grade heat. So how do we make it so we can heat the house? Compress it. So this compressor squeezes those gases, temperature goes up. The more you got to squeeze it, the more you pay. The higher the pressure, the more effort you got to put in. So 45 degrees C comes out as a gas, and it's flowing back in towards the orifice. That's your restriction. We're going to take the heat out of the gas and turn it back to a liquid. All that heat we put in, we're now taking out. Just at a higher temperature range because we compressed it. Okay, so that heat then, we're going to wrap a production loop, another coil around filled with water or antifreeze. And we're going to, just as this a continuous, all 3 loops run continuous, if water's coming in at 36 degrees Celsius through this loop and it sees 45 coming in, which way's the heat going? It's going from the hot gases and the refrigerant to the loop. So the loop now warms up to 40. Come in at 36, now it's going out at 40. So we go into what's called an air handler. It's like a radiator in your car and they blow air across it. It's got hot water in it, okay? So now 40 degrees comes in, but across this, through the air exchanger, we're going to blow 20 degree, that's the return air from your air handler in your house. You blow 20 degree air across a 40 degree coil, which way's the heat? Which way's the heat moving? Okay, we're not going to make it. We got time anyway. Okay, so now you're going to warm the air to 35. That'll heat your house. Okay, and the coolant comes back at 36 and goes around. So we're continuously absorbing, we're continuously reconditioning the heat from a low grade to a higher grade, and then we continually remove the heat and put it in the building. That's a heat pump. It's no more than that. Does that make sense? Now, if we wanted to cool the building, what would happen if we reversed the direction of flow in those evaporator and condenser? What if this was the evaporator and that's a condenser? So instead of going this way, we go that way. This becomes cold, that becomes cold, the air becomes cold, this becomes hot. We pump it into the ground and store it for the winter. Okay, makes sense? Plus the heat from the sun. All right, any questions, thoughts on that? Anybody? Yes.
Is it solely for the purpose of, so you can use it as both heating and cooling during the summer and winter? Like if it comes out at 45 degrees C and then it cools down to 40 degrees, if it's just a heater, why wouldn't you just keep the 40 degrees and then adjust it back to 45 batch?
Because you have to change, you have to raise the pressure, turn it back into a liquid. You're getting a little bit into the physics of it. And in order to do, we have to have a pressure differential between here and here. If we don't have a pressure differential, we cannot have this exaggerated temperature difference. The bigger this difference, the more you pay to run that compressor. So in an air source heat pump, if this is minus 20, you got to pump it up a lot more. That's why it's not near as efficient. It's that simple. It's that delta T right there, okay? All right, now this is water to water, which means you can put the water, this outlet could go to an overhead unit. It could go to the floor like it is in this building. It could go heat and exchanger for your pool, domestic hot water, very adaptable design-wise. Make sense? Okay, whereas this unit happens to be water to air. So now we take the refrigerant and take the heat off the refrigerant directly with air. We don't use an extra water loop. But then the unit's got to be where you need it or pretty close. Does that make sense? Your design limitation. So now if the refrigerant comes in at 45, and don't hold, the numbers all vary a little bit, but for example, and goes out at 40, the air comes in at 20, still goes out at 35. We're just cooling the refrigerant directly with air. Water to air. Make sense? Okay. That's your air source. You got to move a lot of air. This temperature could be minus 30, minus 40, minus 50, because the refrigerant's actually colder than the air. And you got to go to 45. From minus 45 to plus 45 is a 90-degree change in temperature. You are really pumping that bicycle tire pump to get that happening. Make sense? So it's not as efficient. That's why. So if we look at heat pumps and talk about leveraging, reduce the load on the grid, reduce the amount of environmental, we want to look at something called coefficient of performance. How much power do you put in for how much heat you get out? So this company likes to say 5 to 1. You might 30-degree latitude, but you won't up here in all likelihood. I get 4.5 on mine. Okay, so so if you take actual 4 kilowatts worth of heat, the equivalent, out of the ground, but it's not usable, you pay a kilowatt to make it usable, raise its temperature, your total coming out is 5 kilowatts. So you have a coefficient of performance of 5 to 1 for that example. Does that make sense? Okay. So let's turn this on. While this warms up a bit, we're going to just go over there for 2 minutes. I got 2 stations here to do. This is floor heating in here. And so what we do is like I showed you, the one they showed the garage, we embed hot water tubing throughout the floor. And how they do that is they lay it down on the ground, do all the plumbing connections. It comes up over here in this corner, a manifold for access, pour concrete over all of it. Then you end up with this connection, which we'll look at momentarily. And then it's all fed from those 2 blue pipes on the wall. So hot water comes in, circulates through these tubes in the floor, heats the floor up, and then it returns back to the mechanical room to get reheated again and sent back. How do we know we need heat? We have a thermostat on the wall. when it sees the temperature in here getting too cool, it turns on a circulation pump. The circulation pump sends the water through all of these loops throughout this whole building. So I know it's hard for you to see, but I'm sitting here at 20.6 degrees on the floor right now. And it depends where you go, because the loops, if you're between loops, 20.3 over here, too. So the concrete, you can pass that around and shoot the floor if you want. And so what it amounts to is this concrete slab 6 inches thick, and the whole thing is heated up to about 20.5 degrees. It's like a big heat sink, okay? The heat moves up, which is what we want, bottom up. Kick this door open, the temperature drops. As soon as you close that door, you've got all of this massive storage of heat. It just brings the temperature right back up, boom, right now. Doesn't take forever, and it's not blowing down from the top, okay, which is really hard to do. So that's your what's called hydronic heating, and a heat pump, they work great for that, okay? Questions, comments, anybody? Thoughts?
Quick question on the most, I guess, maintenance-heavy components. I assume pumps and compressor.
Okay,
And
on this,
reverse.
you're talking typically a change out on pumps 20 to 25 years on the compressor, okay? You can get control issues. There's electronics on here and, you know, relays and all that kind of stuff. That can happen on any furnace, anything else. So that part, they're pretty robust for the most part. Most of the better manufacturers work pretty good for a good long time. Let me move this out of the way, because I also want you to come up and touch this. Otherwise, you still have a filter that goes over here. You'd have your normal types of maintenance, but I haven't touched mine in 3 years other than filters. Nothing, okay? And the expectancy is 20 to 25 years. Furnaces are what, 12 now? 13? 15 if you're lucky, okay? So if you come on up here, I want to show you both. You can feel the cold air coming in, the hot air coming out. So come on around. You can feel there's only about a 3-4 degree difference between incoming and outgoing. The outgoing, you touch the brass, you'll get a better feeling. The outgoing is a little cooler. So we're taking the heat out of the water in that tank. Our tank is what we're using. And that heat exchanger is called a coaxial exchanger, and it looks, water goes in the middle, refrigerant goes around the outside, and it's in a coil, okay? You can see the compressor in there, looks just like your refrigerator. There's the reversing valve to go from heating to air conditioning. And here's the coaxial heat exchanger right here. Just a tube of that. It's smaller because that's a smaller unit, and it's just wrapped up. So it's about 3 degrees, 4 degrees. This one's a little bit colder. Not much. Hey, well, let's see.
Yeah.
Brass doesn't work, so that's showing coming in at 17. Yep, go. Sorry, yep. Yeah, if you got no questions or anything,
Okay.
thanks.
You guys ready? Thank you, Roger. Thank you, Roger.
Thank you, Roger.
Go ahead.
All right.
Nice.
All right, you gonna
All right.
All right, everybody, welcome. Who here could tell me what the cost of their natural gas is per gigajoule? Not all in, just the natural gas. Anybody know what their utility bills, natural gas per gigajoule cost is right now? Sorry?
Is it $3.40 per gigajoule?
$3.40-ish. Anybody else? I know it's a kind of at one point in Alberta, I think it was 2021. Yep. The price was $13.85 a gigajoule. Everybody flipped. Everybody freaked out. And so everybody wanted geothermal because you heard about the COP, the coefficient of performance, up around 3.5 to 4.5. So everybody all of a sudden wanted geothermal. So in the early days, geothermal was plumber by morning, hooking up like hot tubs, and geothermal expert by night. And so as a consequence, people were not getting quality products. And so sometimes the machines weren't working well, they were falling apart, they weren't working well. Other times, people would eyeball what they should do in terms of the amount of geothermal bore field so that they could get heat out of that. Now, the challenge is they were kind of guessing and using rules of thumb, and some occasional homes in the depth of winter, they would be pulling heat from the ground. And because the ground loops were not sufficient, they were actually freezing up the ground. And so if you want water to come into your house and sewage to leave your house, it's awfully awesome if 6 to 8 feet down, it's not frozen. And that's what was happening. So in the early days, it was a little bit of a Wild West. It looks like Wild West here in the pictures. That's just mud and dirt. And so objectives that Lee really wants us to make sure we cover include making sure we know about the rules for designing and installation. That is not a Wild West. In fact, Alberta has about 4,000 geothermal systems installed to date. The other thing is, we'll talk about matching the amount of heating or cooling a building needs to figure out how big your bore field should be. And a bore field, by the way, is just all the holes with pipes connecting it all up. That's the bore field, it's a field of boreholes. How big a bore field do we need? How many feet deep? How many of them? And you basically, all of your depths multiplied by 2, because the pipe goes down and the pipe goes up. And that is basically your heat exchange with the ground. How big does that need to be? So we'll talk a little bit about that, and then we'll also talk about some of the components. So the rules around doing a geothermal system involve building code. And then the building code refers to CSA 448. Yeah, let me just check that to be sure. Hate to send you wrong. Yeah, C448 is in the CSA standard. And what it says is, here are the materials you should be using. Here are the liquids that you should be using. Usually it's a water glycol mix, but sometimes people use methanol as well. Downside of methanol is it's combustible. So when you're installing it, that can be a problem, but otherwise it works really well. And what are the methods that you should be using as well? Good. So one of the things you need to figure out is, what's the energy load of the building? Then you got to figure out how many boreholes do I need to deliver that. So we would say, for a building like this, we'd say there's a certain heating load on an annual basis. The building has a load or a need for a certain amount of BTUs or thermal units of energy. And so what we'll do is we'll have somebody who is an engineer or an engineering technologist who's been trained to do what's called energy modeling. And so what they'll do is they'll use software. For a home, it's often HOT 2000 is the software that was invented here in Canada. If it is a more complicated building, use something like IES is a really high-end software. You can use others like eQuest. And with those, you can figure out if this is the building, this is how much insulation the building has, this is the location, it's heading towards south, how much window it's got and all the rest of that, where in the world it is, what climate zone. You can calculate how much heat is this going to use on an average year. And you can even say on a really cold year, because our temperatures can vary 15 to 25% from year to year. And the amount of solar light we get can vary by 15% per year as well. Cold years, warm years. As a consequence of that, the engineers have to be like, what if it's a really cold year? What if it's an average year? And from that, you can figure out how much heating does this building need? And then they'll calculate that using the software. Based on how much heat the system needs, then what you do is you go to the actual location where the building is, and you have to figure out, how does that particular geology respond? Does it have a lot of ability, thermal conductivity? Does it have a lot of ability to transfer heat back and forth? Or does it not have a lot? So if it's a wet ground, it's going to have a really good thermal conductivity. If it's very sandy and dry, it's going to have a very poor conductivity. And so what they do is, this is a drilling rig right here, a couple of pictures of it in action. And they'll take this drilling rig over and they'll drill holes. This particular site, the hole's 300 feet deep. And what they did is they hooked up. You can see at the top here, they got a little bit of a white pipe. It probably, I don't know, some sort of plastic. It's just in maybe 2 or 3 feet. So that when they got a big hole, they put that in the top, and then they can feed the tubing in. And as they feed the tubing in off a big giant roll, it gets to the bottom, and then they fill it in with grout to make sure that the pipe actually is touching the ground. Where did I put it? There it is. Ignore the metal thing. This is just so it doesn't get lost, I guess. But basically what you got is high-density polyethylene. So HDPE, high-density, yep. HDPE is just a plastic, but it's really robust. It's really hard to ruin this stuff. And the tube will come down, has a loop at the bottom, or a end on the bottom, and it goes back up again. So of course, you do that up on up on the ground, and then you feed this down. And so basically it goes down and comes back up, and it's totally sealed. And so it's a loop, and that comes down, and then the fluid will flow down through here, comes in, say, cold, picks up heat from the ground, goes down 300 feet, and then it comes back up, picks up some more heat from the ground, and then it goes into the building. We bring a whole bunch of these together. You can see a whole bunch of them coming in from further down, and then you eventually come into a really big version of this pipe called a header, and that header goes to the heat pump. So that heat pump is being delivered heat from the ground, as we were saying, maybe 7 or 8 degrees Celsius, and then the heat pump upgrades that to, say, 35 degrees Celsius, heats the building, comes back at a low temperature, and picks up more heat, and then this fluid, though, keeps flowing back down into the ground, picking up more heat, coming back up, going back into the ground, picking up more heat, coming back up. Have a look. Pass that around. So what they figured out is that stuff is going to live forever. And so they've done some tests where they've dug up stuff that's 50 to 80 years old. It's fine. They've done others where they put fluid through it at a super high velocity to do destructive testing at high velocity to what if it was more years, and they calculated a ridiculous number. And so basically, if you've put in a bore field and the building burns down, you build a new building and hook it back up. And then 80 years later, the building needs a replacement because it's just really old. Tear it down, put in a new one, but hook it up to the same geothermal system, because that'll probably last for about 300 years, give or take a couple hundred years. And so the consequence of that is unlike your house where your furnace has to be replaced all the time, this geothermal asset is going to be permanent, and you're going to replace the building all the time. So it's a very different way of thinking about heating and cooling. So all that said, once they have done those calculations.
Actually, not replacing the building all the time.
No, like
Deep retrofits.
like every 50 to 60 years. Yeah, 60 to 80 years, exactly. And so that's the other thing is if it's a brand new building, they'll do all that design work. If it's a retrofit building that you want to make perform better, they'll do the analysis, figure out what is it using right now, and then maybe make recommendations on making the building better as well as the geo. Rarely do you just do geothermal into a leaky, crappy building. You probably want to make the building a bit better. That brings us into the optimization thing that I'll talk very briefly about, is that if you increase your insulation, at some point, the amount of energy savings from more and more insulation is a bit of a diminishing return. And so if you're hitting like R28, R30, you're getting really close to the limit of how, if you add another inch of insulation, it's not going to make a lot of difference. If you add another foot of insulation, it's not going to make a lot of difference. So at some point, insulating more is not going to give you anything but a bigger end of the day bill. The geothermal is really expensive to do on the capital, like the very first cost, the capital cost, the sticker price is very high. People have a heart attack. And if you can reduce the amount of geothermal you need, that's great by increasing the amount of insulation. But at some point, there is diminishing returns over there. And so your engineering firm would be calculating back and forth for this particular building, this heading, this climate, this number of windows, et cetera. They're going to optimize that, and there will be an optimal point between the amount of insulation and tightness of the building versus the size of the geothermal bore field. Again, this particular one, here's the picture right here. You're going to go outside and see a little bit, but you can see there's actually these boreholes all around the side of the building, and then they afterwards, they went and they paved over everything. And you can see all these lines are coming back and eventually come into the building. And I think we saw a picture from Lee earlier about that doorway where all those pipes come in. It's quite a nest of pipes coming in, but it's all underground now. Okay, so then the next thing is that some people are like, oh my goodness, but it's so cold here in Alberta. So here's our interactive part of the show is I'm going to give you 4 options. How many days of the year is Edmonton below minus 30 for the average year? How many days of the year, and I'll give you some numbers, how many days of the year are we below minus 30? Is it A, 20 days, B, 10 days, C, 4 days, or D, 1 day? And on the count of 3, we're going to all say out loud what our number is so nobody can tell if anybody's wrong. Ready? On the count of 3, 1, 2, 3. Okay, the answer is 4 days. I see some engineers in the crowd. Get out. No. Okay, so 4 days is not actually 4 days in a row. It's 92 hours, usually at like midnight till 3 in the morning between December and February. And so It's not hyper super cold, but the other thing is it's not getting colder, it's getting warmer. So this is a graph showing you how many minus 35 days do we have per year in Edmonton, and you can see over time, it's getting warmer and warmer and warmer here. I don't know why, it's just what could be happening. But then the other thing is, at the same time, the number of heat wave days, which is 2 days in a row or more, the number of 2 days in a row that's above 29 degrees Celsius, but at night it doesn't get super cold. And then it's getting harder and harder to stay cool, right? Harder and harder to keep the buildings cold. And you can see there is a definite trend of how much cooling we require too. The nice thing is that the heat pumps, air source or ground source, can give us both heating and cooling. So I'll show you that. So heat pumps could be a really good solution as we move forward. So the energy supply, as we said, is a ground loop. We have to figure out how much heating does this place need or cooling. Then we go and drill one single hole. So they'll drill one hole, then they hook up to that something called a thermal conductivity tester. And the TCT is hooked up and it puts a very specific amount of heat down the hole. And then that bore field or that bore hole, the soil around it is going to absorb the heat. So you put the heat down with a known quantity and you see how much heat comes up the other side. And then you run that for like a day and a half or 2 days, you do some calculations and you figure out what is the thermal conductivity of that soil. Then you go back and you calculate a bunch of stuff and you find out if we need this much heat and the ground can absorb a certain amount of heat, then, or give a certain amount of heat, then how many bore field, how many holes do we need and how deep should we go? It really is just a total length, but sometimes they need to drill extra deep. It gets more expensive the deeper you go, but they might have to drill extra deep because they have a small footprint to work with and they can't, have 48 holes. Maybe they can only do 36 holes, so they have to add more depth. And so those are the calculations they do on the back end, and then they come back and start drilling all the holes. This particular building, 48 holes, 300 feet deep, and it takes a day to a day and a half to drill a hole at that depth. And so they had two different teams, sort of the battling banjo thing going on, to get this all done on time.
Question. That piece right there,
Yes.
are they always straight or do they ever make them cyclical so
Right.
that you have the gas, whatever, it's like the water, whatever is being
Yeah.
heated up is spending longer underground so you don't need to drill as deep?
I do not know. That sounds exciting. Yeah. There's some that use a 4-loop system and some use a 2-loop, a 2-loop 4-pipe or a 1-loop 2-pipe. I've heard of those, but I've never seen a helical version, but that might be really cool. Last couple things to say, net zero. This building may or may not be at net zero. We're going to find out in the next little while. That is my phone going off. Perfect timing. Give me 1 second. I'm going to guess that it's my wife going, you are almost done, right? And she is right, because we are almost done. So net zero. Now, not only we're trying to optimize for the amount of insulation and air sealing, but we're also trying to, and the geothermal amount of geothermal, we're trying to optimize those costs, but now we're also trying to optimize the amount of solar because that's usually how we're going to get that extra, that electricity that's low carbon. And so now we're getting into that solar question of how much solar should we have. And again, the smaller the bore field, not only are we going to save money on that, but we also will require less solar as well. And so that's sort of, but you don't have to have solar for geothermal. You're taking electricity from the grid, but you can also use solar. So there's additional optimization that might be needed there. The sticker price, like I said, is the hard part. And so I did a retrofit on my house, 1948 house. We did make it net zero. We went really deep on the amount of insulation on the walls. And I opted actually for an air source heat pump because I just did not have the available capital. But if you do, you'll find that the cost, all-in costs of not just the first sticker price, but also the cost of the electricity, the fuel to run the system, and the amount of maintenance and other things all should be factored in there as well. So we will call that a life cycle cost analysis. As you look across the life of the entire building and do a life cycle cost analysis, maybe you have to replace some parts every once in a while, and you calculate it all out, your full total all-in cost with geothermal tends to be a lot less than the air source heat pump. It's a question of, do you have access to enough capital to get that system put in. And so one of the people is here today, Barbara Daly. She is with the City of Edmonton, and they have a program called the Clean Energy Improvement Program. And it's a low-cost loan system. If any of you are from Calgary and a number of other towns and cities in Alberta, they also have SEEP, as we like to call it, very similar to PACE in other jurisdictions. And that program allows you to borrow money at a relatively low interest rate, but you pay it back on your taxes rather than having to pay it to a bank. You pay it back to the city through your taxes, and you pay it out to a known amortization length of time. But if you want to pay it back early, you always can. Where if you do that with a mortgage, you're paying a penalty. And so there's some interesting different programs that are now being rolled out. Rather than here's money for free, that would be a grant. Now a lot more is funded through things like low interest loans and things like that. All right, so that's everything I've got to say about this. Next up, Tom, you're going to point at where all these things are and then take them into that giant room where the heat pump magic happens.
Not really a giant room, but follow me anyway.
All right, thanks all.
So just sort of pad lightly so you don't get so you don't fall down on ice. I've been out here, it's slippery. You can see where I've got my signs. The wind's blown over some of them, sorry. But anyway, those are the loops that Jim was just talking about. Looks just like this. This loop goes down 300 feet, okay? That's what it looks like. Down this side of the building, I've only got 8 signs up, but it goes, the boreholes go all the way down to the fence. They're about 20 square feet apart, so you can grab enough heat or push enough heat back into the ground. There's, on the west side, there's a loop, and on the other side of the building, there's a loop. So that's basically what the loop looks like. There's 48 boreholes going down 300 feet. That's an engineering calculation that was done based on the ground conductivity, the type of fluid they're using, the size of the building, and how much heat they could get from the earth. Remember, as you heard the first station where the heat pump was, in the winter, we take the heat out of the ground and put it in the building. In the summer, we take the heat from the building and put it into the ground. Right now, below my feet, 250 feet down, the temperature's 6 degrees, 5 degrees, and it's that same temperature year round. And that's the bonus that allows us to use a geothermal heat pump. You did hear about the boreholes that go down, and I think Jim briefly mentioned you could lay a horizontal layer down. That's perfectly acceptable. If you put the first layer down at 9 feet, you could actually put earth on at 3 feet or 6 feet and lay another row of loop down, and then at 3 feet, fill that up again. So you could actually have 3 horizontal layers. So if you have a farm or a big property with lots of land, you can do that. Here, if you look at the square footage of the site, there's not that option of land, so that's why we go straight down. These boreholes are very common now. A big city like Vancouver, where they have office tower after office tower, all the office towers now are running heat pumps, and they take their heat from the building in the summer and they cool the building by pushing the heat down into the ground. In the winter, they take that heat out of the ground and put it back up into the building. One of the interesting phenomenons with having so many very large office buildings, very tall office buildings with all those boreholes now is once you push all that heat into the ground, the heat from this building is going into the ground, the heat from this building is going into the ground, and they're sort of fighting each other. So you have to be very careful when you're sizing these and knowing where to put the heat below the ground. Some engineers are getting very crafty. Instead of using boreholes into the ground, and you can only do this in a place like Vancouver, they'll bring the water out, let it cascade over a 20-foot high waterfall with a little collection pond on the bottom, and that's how they're getting rid of the heat from the cooling. They're just using a large pond. And I've had a couple of installations on Vancouver Island where we don't use a large pond, but we sank our heat source into the ocean. right? So at BC Ferries, if you ever go to Departure Bay and you sit there where the food court is and you look out over the bay, if you go out there and about 45 feet down, there's a huge rack that's about half the size of this parking lot here, and it's got tubes that were just like this. They're just a little bit configuration. They're just circular tubes. And that was like 10 years ago. So by now they probably got barnacles and fish all go through them and all that kind of stuff. That's probably it for boreholes. Walk carefully to the door because I don't know where exactly the ice is, but there was 4 patches of it. So just be careful. And as you're walking to the door, look up here and you'll see our solar on the south side. It's really good to have it right on the south side. Boom, you get the heat, even the low heat in the winter. Oh, bonus. You can hear the heat pump running. It's not this compressor, it's the other one deep inside. Somebody did mention about inside of a piping. You can see, I think it was you. No, who was it to mention about the inside of the piping? Somebody mentioned he's outside looking at the solar panel, unless he slept. But you can see this here is heat exchanger on the ground, which is just those there. They're all covered with insulation. But you can see the refrigerant goes around the inner part, but you can see the inner part has a spiral. So the spiral helps make the water turbulent and pick up more heat. Got really close, right up. You can see right there. Good. So if you remember the at the last station, you'll see the pictures where the piping came up through the ground. That's that header there and the back one. And if you see the arrow on the piping, it comes up, across, goes into the heat pump, and the station with the heat pump, he gave a very, very good detailed explanation of a heat pump. We add heat to the compressed gas in here, then all that heat goes to buffer tanks on the far side of the room. We got 3 200-gallon tanks. That's just to help maintain a certain mass of fluid always going out to the system.
Sorry, is the buffer tank for the refrigerant?
I'm sorry?
What is the buffer tank used for?
The buffer tank is just hot propylene glycol. All the refrigerant is in this little cycle, and then the exchange medium going into the earth is methanol. And methanol is used because, number one, by volume for the amount needed, it's less expensive than propylene glycol. And number two, it's less viscous, so you need a small pump, or you could use a small pump. And that's one of the ideal, or the best ideas of this simple system is it's got small horsepower pumping right throughout the whole building. Okay? That's pretty much it. Heat from the ground, put it into the building. I think you saw right behind you, there's another header there for going out into the building. One of the simplest things about this, of course, is right on the wall here, you can see the type of thermostat that measures the water temperature. That's it. Really, really simple. I mean, we could make it more complicated if we wanted, but there really isn't a point. Because
Awesome.
any questions?
So there's 2 heat pumps in here?
There's 2 heat pumps, and each pump has 2 compressors. Okay. So really, you got a total of 4 stages if you needed it. Remember, when we heat the mass of that concrete up, we're good, because that concrete will take, depending on outside temperature and the ground temperature, probably take 8 to 10 hours before it got cool. And actually, anybody that sits outside in the sun on a rock, well, look where all the snakes and the reptiles go. They go sit on a rock in the sun. It's nice and warm. Any questions? This is the command center for the whole building. So if you think about how simple this is, it's pretty simple. That's the neat thing about it. It doesn't have to be complicated.
Does each of those boreholes go straight here, or do they connect to each other?
The boreholes go down 300 feet and come up, and then when they come up here, they all join underground and collect, because there's 48 of them. So they all start collecting, and by the time they come up here, there's only 4 on each side, 4 from the east and 4 from the west. Okay, and if you remember going out there when at that very first station, remember the color of the pipe you saw out there? Well, this is it here. And actually, everybody come by here and touch this pipe. Feel the warmth of that pipe. That's our heat pump that's working right behind me. That's probably very similar to what you saw at that first station. So that's water going to the buffer tank. And if there's any zone out there that needs heat, the thermostat will say, oh, the water's too cold. I'm going to turn the pump on, and then the pump will start pumping this temperature of water through the hydronic system. Now, if you want a room to be 22 degrees, in your floor, you only need to put 23 degrees, not much more. Doesn't have to be that much more. Whereas if you use air, you've got to put 80, not 80, but maybe 70 degree air or 60 degree C air into there just to keep us warm. And the neat thing about hydronic heat, when your floor's warm, the heat comes up and it warms up the table legs, the table, the chair you're sitting on, all that stuff. So it's a heat that really envelopes you, right? Really good. Any questions?
You have zones? Like here it's a warehouse, so I assume it's like one zone.
No, he's got it zoned because
Yeah.
this header does this part of the warehouse. And remember the station where he was talking about the heat pumps? There's a header there. There's a header there. So he's got 4 zones just in the warehouse itself.
That he can control.
Pardon me?
That he can control.
Yep, that he can control. Each one of them is controlled just like this, with the thermostat controlling the pump there. Yeah, so he can do that. When you get to the offices, that was an older part of the building, and he couldn't put in a hydronic system then, so he went with the overhead air. Good?
Thank you.
It is cool. Very cool.
Thank you.